Okay, so when we talk about the relative age of something, we're talking about something compared to something else. What is older, what is younger, etc. This portion, we're going to talk about what's called absolute age. All right, being able to find the approximate number of millions of years ago that something lived. We call that radioactive dating. You may have heard of called carbon dating, but there's more than just carbon that we use to date things. Okay, it's the number of years ago an event occurred or an organism lived. Right? And we're going to use the concept that elements, some elements left alone will turn into other elements. They're not stable. Right? And the element that we start with is what we call the radioactive element or the parent element. And what it turns into, if it's left alone, turns into what's called the decay element or the daughter element. All right. That decay process gives us a number that we call the half-life. Right? It's the amount of time it takes for half of a radioactive element to change. Okay, this is a great way to find the age of things. Nothing affects radioactive decay. Right, so if you look at this graph, right, let me try to decipher this graph for you here. All right, 0 time units, that's the beginning. So we think about, I'll use an example, I'll use carbon because everybody knows carbon, all right? Living things have carbon in them, but they have different types of carbon, all right? The carbon that normally exists that we deal with on the periodic table is called carbon 12. All right, it has 6 protons, 6 neutrons in the nucleus. Well, there are other forms of carbon, and the one that's important to us in terms of finding out how old things are is what's called carbon 14. Okay, it has 8 neutrons. It's called an isotope. All right. And when you are alive, or when an organism is alive, it has a certain amount of carbon 14 in it. But as soon as it dies, that carbon 14 starts to decay into something called nitrogen 14. All right? So 0 is essentially when the organism dies. It's the start of death, so to speak. All right? So it has 100% carbon 14 in it when it dies. That's how much carbon 14 it has. All right? Every half-life, okay, it loses half its carbon and turns it into nitrogen. So if you look at this graph, we've got 20 atoms, so to speak, of carbon 14 and no atoms of nitrogen 14. After one half-life, now we're down to half the carbon. We've got 10 carbon now. And those 10 carbon that changed turned into nitrogen. Well, another half-life has passed, so we're down to 50%. Now we're down to 25%. Look what happens, okay? Those 10 turned into 5, and those other 5 got added on here. So look what's happening. We're going from 20 to 10 to 5 to 2.5, et cetera, et cetera, et cetera. This line, theoretically, is never going to reach 0. Right? We can always take half. Right? And the nitrogen it turns into is going to get more and more and more as we go. All right, that's kind of what's going on. And knowing how much carbon 14 in relation to how much nitrogen 14 is in something, we can backtrack and figure out when it died. All right. All right, here's another way to look at it, okay? Carbon 14 has a really short half-life. It's used to date recently living things, wood, bone, stuff like that. Page 1 has half-lives that we use in here. If you look up here, see these guys up here? These are 4 different radioactive isotopes that we use to date things. Carbon 14 is the most popular, most common that we use. It's used for very young things, things that aren't older than about 50,000 years old. Right? Here's what happens. You start with carbon 14. Here's what it turns into, nitrogen 14. And here's how long each half-life is. 5,700 years. 5.7 times 10 to the third is 5,700 years. All right? I'll write that over here. 5,700 years. Okay? What that means is that every 5,700 years, we have half the carbon-14 left. And then another 5,700 years, we have half of that left. And then another 5,700 years, we have half of that left. So we keep taking half the carbon every 5,700 years, and that amount gets transferred over and becomes nitrogen-14. Right? That's called radioactive decay. It's a very stable rate. All right, here's a little model to show what we've got. So at the beginning, we have all parent material. All right? After one half-life, and again, the half-lives are different, okay? Carbon-14 is 5,700 years. Potassium-40 is 1.3 billion. Uranium-238 is 4.5 billion. And rubidium is 49 billion. So depending on what you're doing, you're going to use different things to date different things. There's lots of other ones too, but these are the four they put on the reference table, so these are the only four you have to be responsible for, okay? Carbon-14 turns into nitrogen-14. Potassium-40 turns into either argon-40 and calcium-40. Uranium-238 turns into lead-206. And rubidium-87 turns into strontium-87. Okay? So, after one half-life, whatever that may be, if you're doing carbon, it's 5,700 years. If you're doing potassium-40, it's 1.3 billion years. It's whatever, you have to know whatever you're dealing with, all right? So, we're going to have half the parent, and then the other half is going to be daughter. After two half-lives, we've got half of the half, which is a quarter. The rest of it is daughter. After three half-lives, we have half of a quarter, which is an eighth, and the rest is daughter. See how it's getting less and less? The parent isotope's getting half each time, okay? And then the rest of it becomes daughter, right? So if we were to put a little dot on top of these guys, look what we get here. We get a graph that's getting less and less and less, but it's approaching zero, all right? The numbers at the bottom show the ratio. We have 1 part parent to 1 part daughter. After two half-lives, we have 1 part parent to 3 parts daughter. After three half-lives, we have 1 part parent to 7 parts daughter. And then we have 1 part parent to 15 parts daughter. And it keeps going like that, all right? All right, let's take a look at this. So I'll show you kind of an example, all right? Got a little table here that I put together. All right, so we're going to use, we're going to use carbon-14 turning into nitrogen-14, okay? Because that's the one everybody knows about. Everybody knows about carbon dating, all right? So let's say when the organism dies, it has 100 grams of carbon-14 in it. That represents 100%. All right? Don't worry about the ratio for right now. Let's just do rest for a second, okay? So if it just died, it doesn't have any nitrogen yet. Okay? So no years have passed. It just died. After one half-life, so carbon-14's half-life is 5,700 years. So 5,700 years after that organism dies, it now has half of what it started with. That represents 50%. All right, these are some bad numbers. I'm going to use a better number. Hang on. Let me use some better numbers. Okay, still zero there. Let's say 40 grams of carbon-14 represents 100% of the carbon that it has in its body. All right. After one half-life, it's lost half, so it's down to 50% carbon, which is 20. All right. That 20 grams gets added to the zero. We now have 20 grams. Okay. Don't worry about the percent for a second. We'll work with that after. All right, so now let's just stick with the left here for a second. 20 grams, 50%. Now one more half-life. So we're on 2 half-lives now, which is 11,400 years. Okay, 11,400 years. Now we're down to 10 grams, which represents 25%. Those 10 gets added on over here, and now we have 30. All right, let's keep going. 10 grams, one more half-life, so 11,400 plus 5,700 is going to be 17,100 years. we're down to 5 grams. Now, 25%, half of that is 12.5%. Those 5 grams that we lost get added onto here, and we're now at 35 grams. I'll get rid of this for a second because I don't want to use anybody. All right. Okay, so one more, 17,400, another 5,700 years. What is that? What's 17,1? What's 5,700? What do we got? 22,800. 22,800. Half of 5 is 2.5 grams. That 2.5 gets added onto here, so we're at 37.5. That represents 6.25%. Let's do one more. 22,800, one more half-life. What's that? 28,500, 20,500 years. 2.5 is going to be down to what? 1.25, right? That 1.25 goes on to here, so what's that? 38.75 grams here. And we're down to 3.125% there. Right? Notice how in this column, the number of grams of carbon-14 got less and less and less. The number of grams of nitrogen got more and more and more. But notice when you add them together, they are still going to be 40 grams what we started with. All right? So 100%, 50%, so 20 is going to be 50% here. 25% here, so we have 75% here. 12, what's that? 87.5 here. Let's see, 87.5 and 6.25. What do we got? 93.75. And then we add 3.125 onto that, we get 96.875%. Right? What's the gist of this right now? Okay, whatever you start with, every half-life, whatever it is, the time goes up by whatever the half-life is, and the amount you have gets less and less and less by a half. All right? I'm not going to worry about the ratio column. You don't need to worry about that. Okay? I don't even use that one. All right, that's good for now. And that. I know it seems a little complicated, but as we start to do things, you'll see how it kind of falls into place.